Let's talk about the Brinell hardness test. So the Brinell hardness test was really the first common hardness test. It came around 1900. It was invented in Sweden by a Swedish guy named John Bernell. So he came up with a great idea. Basically, what his idea was, if you take a really hard material and smush it into a material that's not as hard, the not as hard material will have a dent. Just like if you take a piece of diamond and you scratch a piece of glass, which one gets scratched? The glass, right? So it's the same idea with the hardness test. So what he used was a 10 millimeter ball bearing. So ball bearings are always very, very hard materials. They're harder than just about everything, especially at the time when they didn't have as many materials available. That's what he used. That's what we still use today. It's 10 millimeters because Sweden, European, they use the metric system, and we use kilograms of load to measure how much force we're applying as well. The Brinell hardness number is totally arbitrary. Basically, people agreed that if you get this big of an indent on iron and this big of an indent on aluminum, we're going to assign them numbers and we're just going to use those numbers. What happens is with a 10 millimeter ball and 3,000 kilograms of force, we'll get an indent. The larger the indent, the softer the material. If you get a 10 millimeter indent, then that material could be either at the bottom end of the Brinell hardness test, or it could be so soft that the ball punched all the way through, in which case the hardness reading is totally null and void. If you get a very small indent, too small to measure, it means the Brinell hardness test is at the very top of its useful range. So we can fix this using the Brinell tester by either using less force in a 10 millimeter ball for really soft materials, or a smaller ball and the same amount of force to apply more stress at that area to get a more accurate indent. By far the most common is 10 millimeters, 3,000 kilograms. That's what we'll be using today. So unlike Rockwell, this style up here doesn't tell you anything except the load you're applying. To find the actual Brinell hardness number, we have to measure the indent. So just like they can measure the diameter of a crater and kind of figure out how big the meteorite was or how fast it was going, we're going to measure this indent to see how hard the material is. Now there's a formula for it, but it's also on standardized charts. There's a chart in the back of the machine. It gives you the hardness value for a set load and a set diameter of an indent. The way we measure the indent is with a microscope. The manual ones look something like this. There will be a light that plugs in here so you can see what you're doing. You'll look through here. You'll line up. There'll be a graduated line on the inside of this. It's similar to an optical comparator. So you line up the 0 on the graduated line with one side of the indent, and then you get as close to the center line of that diameter as you can, so you're getting the maximum diameter, and you see what where it reads on the ruler. So it's going to read in 0.1 millimeters. So you can get 5.1, 5.2. You get 2. You can't get any less than a tenth. So you won't have 5.15 readings, right? Just one decimal place is good enough. You'll take that, you'll apply it to a chart, and it'll spit out the Brinell hardness number. So the way the actual test works, it's pretty simple. We got a switch on the back of the machine. This particular machine looks like a light switch. I'll turn it on. It'll kick on a hydraulic motor, and it's ready to do its thing. I won't turn it on quite yet because of the sound. I've got a handle here. When the machine is on, I can adjust the amount of load it applies. So since we're using 3,000 kilograms, I've already got it set. That red arrow lets me know where to set it when I'm doing it. This button right here will apply the load, so the stroke will go down and it'll press into the material. We'll let it dwell for 10 to 15 seconds. After that, I'll release it and then roll this down. One thing about Brinell, you can't test really thin materials, and you can't test anything that's not flat and parallel. So only rectangular objects can go in a Brinell machine, whereas a Rockwell tester has a special setup to do cylinders. I'll get a piece of material. This is really about as small as you want to go. The less material you have, the less the ball has to push against, and it'll give you a suspiciously low reading. So I place the material on the anvil. I'll move it around, make sure it doesn't rock, make sure there's no dirt or debris or anything underneath it. I'll move the anvil up until it touches. Unlike Rockwell, there's no minor load, so I just need to make sure it touches and it's good to go. So the next step, I'll turn on the machine, I'll apply the load for 15 seconds, I'll release the load, turn off the machine, lower the anvil, and then I'll measure the indent. So I'll do that now. Turn on the machine. So I got the machine on, the anvil's set. I know this is already set, I've done it before. I'll hold down the button. I can watch this go up to 3,000. I know I'm applying the appropriate amount of load, and I'll wait about 15 seconds. I'll release the button, the load is off. I can turn the machine off. I can lower my anvil. And I've got a nice indent into this material. So I would take this, I'll measure it with the microscope and see what the diameter is. Then I'll just plug it into a chart. There's one on the machine, they're available online. The one you trust the most is ASTM E10, Bernell Hardness Test. It has the official numbers. So that's a Bernell Hardness test, not much to it. They're great for softer materials, so brass, bronze, iron, aluminum, lead, zinc, tin, materials like that. The downside is that it's a little bit more time consuming, even with an electronic measuring device to measure the diameters. A little bit more time consuming than Rockwell. If you remember, Rockwell reads right off the dial, so a little faster. They also leave a larger indent than a typical Rockwell tester, so it could damage material. You know, it depends on your surface finish requirements, but having big dimples all over parts going to customers could be an issue. Whereas Rockwell Vickers or Rockwell Superficial will leave much smaller indents that might be unnoticed. Okay?